Okay, thanks. So what I'm going to explain to you is this is a continuation of Henri's talks. So I hope that you remember some of what he talked about. But what I want to talk about is the relationship between information and communication for communication protocols, for interactive communication protocols. So let me just remind you of what those are and what we know about them to set the context, and then I'll focus this whole talk on one result about this relationship. Okay. So first, what's a communication protocol? So we have two parties, Alice and Bob, that have two inputs. So Alice has X, Bob has Y, and they exchange messages in order to compute something about these inputs. Okay? So Alice sends a message that depends only on X, then Bob responds with another message, and so on. So here, these messages, so I'm imagining there's a distribution on inputs. So there's a distribution on inputs X and Y. And these messages may also be probabilistic. Okay, so for each X, Alice may sample from some distribution and send a message that depends on her input. Okay, so the communication complexity of such a protocol is just the length of the number of bits that need to be exchanged. Okay, so the maximum number of bits that might be exchanged in any execution of the protocol. That's one measure of the complexity of this protocol. And another measure, one that we've been talking about, is the information of this protocol, which is this quantity. It's how much do Alice and Bob learn from taking part in this protocol. So Bob knows Y, and he learns this many bits of information about X by taking part in this protocol, and Alice learns this many bits of information about Bob's input by taking part in the protocol. So that's the information. Now, in talking with you guys, or especially some of the information theorists in the audience, several people have asked me many different times why this definition of information. And I think that's, in information theory, people come up with many different concepts for information, and they study, different ways in which they operate and different relationships between them. But so people have asked me, why are you just obsessing with this one definition? And I'll tell you why. It's because we're not actually interested in this definition. What I actually care about is understanding communication complexity. I want to understand the complexity of solving all kinds of combinatorial problems where there's no definition of information. Okay, so the problems have nothing to do with information, but all our methods for solving those problems seem to converge on this definition of information. Okay, so it arises from the problems. It's not something. It's not a choice to use this definition of information. It just shows up in the problems. So
in other words, you actually can the result that come out of this you can actually use as for proving them lower bounds or something.
Yes, exactly. That's where that's slide 2. Slide 1. Okay. So slide 2, for example, this definition shows up when you try to understand the randomized communication complexity of disjointness. That's a problem that, for example, Stefan uses a black box to show all of his results, right? But it's not just used in distributed computing. The randomized communication complexity of disjointness is used to understand the complexity of data structures, to understand the complexity of monotone circuits, in many different diverse areas which seem completely not connected to each other. They all use this as a black box, which means that they use this as a black box, because the only way we know how to prove a proof is using this concept.
Is it fair to say that, even though you can discuss on what would be the proper definition, this is undoubtedly a lower bound on that information. And if you're interested in lower bounds, then this is undoubtedly a good concept.
Yes, right. Ultimately we're interested in lower bounds of the communication, and all the proofs we know work by understanding this. So that's true of a number of combinatorial problems that don't have anything to do with information. Okay, understanding the role of the number of rounds in communication. And it also arises when you look at, for any problem F, if you look at the amortized communication complexity, namely the communication complexity of computing n independent copies of this function divided by n, then this limit turns out to be exactly the information cost of the cheapest protocol for computing the same function. Okay? So it's another way in which it arises sort of independent of any concepts of information. And finally, a very related result is that we know that these concepts are more or less the same if you're just talking about one-round communication. So if you're just talking about one message that Alice is sending to Bob, then you can always simulate any protocol that looks like that using a number of bits that's actually close to the communication, to the information. Okay, so it seems this number is always less than the communication complexity. And for one-round protocols, we actually even have a converse. Okay. So also, yeah.
But there was the achievability there would be plus square root I.
Yeah. So I should write here order.
Yeah, that's fine.
Okay. So they're order terms. So maybe I'll make this a squiggle. Okay. Okay. And moreover, up to very recently, all the methods we know how to prove lower bounds for communication, at least in the randomized communication, they also tended to give lower bounds for information. Okay, so all our methods for proving lower bounds actually ended up proving lower bounds for information also. Okay. So it seemed like these two, it seemed like a lot of evidence to suggest that these two are the same. Like morally, this number is the same as this number. And what I want to show you today is a beautiful result that proves that they're not the same. In fact, they can be very far apart. Okay, so that's a theorem proved in a sequence of works by Ganor, Cole, and Raz. But the proof I'm going to show you today is a recent paper, myself and Sinha, where we simplified the ideas that go into this proof. Okay, so I'm going to show you a purportedly simpler proof, but I will say that it's not simple. Okay, so I think a major open problem here would be just to find a nice, elegant proof that shows that these two are not the same. But let me tell you exactly what we're going to show. So what you can show is there's some function f such that that can be computed with I bits of information. But it requires 2 to the omega I bits of communication. Okay. So there's an exponential gap between these concepts. There's a function that can be computed with information I, but to compute the same function using any protocol, any communication protocol, you have to exchange 2 to the omega I bits of communication. Yes, it's in the next slide. So let me just tell you, so in general, you can ask, given any protocol that has I bits of information, how efficiently can you simulate that protocol? And this shows that you cannot hope to simulate it with I bits of communication. But let me tell you 2 results, at least that go in this direction. So the first, so suppose you have so the claim is that if you have a protocol with I information and C communication, so the first result that I want to tell you was the first result that we proved about this, is that you can simulate it. So it can be simulated with square root of I times C log C communication. Okay, and this is work with Barak, Brewerman, Chen. And then Braverman also proved that you can also do such a simulation with 2 to the order I communication. Okay, so here are 2 bounds that show that there are some simulations, and we don't know. And what this result says is that this bound or this kind of bound cannot be improved. Okay, so it says that basically if you take this function, then there's a protocol that computes it with I bits of communication, and you cannot simulate it with better than 2 to the I bits of information. You cannot simulate it with better than 2 to the I bits of communication.
Can you say in advance what is the amortized complexity for this problem?
The amortized complexity for every problem by this line is equal to the information. So even for that problem. Okay? So in particular, this is a problem for which the amortized complexity looks very different from the one-shot complexity. Okay? Okay, so the point is that here there's a dependence on C. And when you have a dependence on C, you can hope to get some kind of compression results, because that does not contradict that statement. But if you don't have a dependence on C, then the best you can do is an exponential dependence on the information.
But you might have a small dependence on n.
There's no n, C.
No, I'm saying suppose the length of the input is n.
Uh-huh.
So okay, if you have a small dependence,
You might have a small dependence on n, yes.
then we can still relate it to r.
Yeah. So there might be, so right. So that's the space of thing that's open. So this is, as far as we know, essentially the only result that handles the general case. So one open question is to improve this bound. And another open question that would be very interesting for me is to simplify or give a nice proof of the thing that I'm going to show you now, next. Okay, so what I'm going to talk about in the rest of the talk is the proof of this result. No. All the parameters are the same. It's just that I can now communicate the result. So I compressed the paper, not the protocol. Okay, any questions or comments before I continue? Okay, so I'm going to describe this result. I won't be able to do all the details, but I'll try to give you a high-level overview of what the problem is. You know, all of these facts, they put a lot of constraints on what this example problem must be, right? For example, this fact, the fact that information and communication are roughly the same for one-round protocols means that somehow the protocol which achieves low information must be a very interactive protocol. Right? Otherwise, I could apply this, okay, and it will be a very interactive protocol. So the other thing that I wanted to comment about this. So this means that, you know, this was true before, but in particular, this result means the only way you can prove that result is by proving a lower bound on communication that does not apply to information. Okay. Right? Because you have to separate the two. So in fact, along the way, these guys discovered a new way to prove lower bounds in communication protocols that does not prove lower bounds in information. Nevertheless, you'll see, the lower bound uses a lot of ideas from information theory. In fact, it's almost all information theory, which was somewhat surprising to me, at least, when I saw it. Okay. But we'll see how. It's actually, it reminded me a little bit of how in Andre's talk, he described a proof for the non-Shannon inequalities, but then the proof went by using Shannon's inequalities, right? Because you made this proof, and then you just deleted one term by changing the probability space. And in fact, at a high level, that same thing is going to happen here. So we'll have a probability space, then we'll look at a different probability space, do all kinds of information stuff, and then we'll change the probability space. How the number of rounds. So in general, so what you can say is that C is bounded by order I plus the number of rounds. Okay, so if if the number of rounds is comparable to the information, you're in good shape. But in this example, the number of rounds will be exponential. Yeah, it's unclear what the actually also here this C you can replace the number of rounds. This is actually the number of rounds in both of those terms. Other questions? Okay, so let's take a deep breath and start writing many equations. So first I'll describe the communication problem, and then we'll start arguing about it, or the problem. So what is the problem? So in the problem, it looks like this. So Alice and Bob are given as input two functions. Okay? So Alice will be given a function mapping the set 1 to k, strings in the set 1 to k of length less than n to a symbol from 1 to k. And Bob will be given a different function that does the same thing. Okay, so this thing is strings of length less than k, less than n. Okay, and actually, so I'll write things in terms of n and k, but throughout, what will happen in the end is that n will be set to be 2 to the 100k. Okay, but I just don't want to write 2 to the k everywhere. So you can think of it like that. So there's a small alphabet, and you have long strings, and Alice and Bob have functions that map each string to another symbol. And they also have an additional function. So Alice has a function f that maps strings of length n to a bit. And Bob has a function that maps strings of length n also to a bit. Okay. So those are the inputs. Now I'll tell you what their output is supposed to be. So to define their output, let's define z sub r plus 1 to be x of So what I've defined here is a string of length n in this alphabet, which satisfies these n equations. Okay, so the first symbol of the string is you just take x of the empty input plus y of the empty input mod k. That's the first symbol. Then you take that first symbol and you evaluate x at it and y at it, sum them up, you get the second symbol of the string. Okay, so now you have a string of length 2. Then you evaluate x and y on the string of length 2, sum them mod k, you get the third symbol. You do this all the way until you have n symbols. Okay, so this defines a string of length n. And the final output is just, they want to output f of z plus g of z mod 2. Okay, they want to output the parity of f and g on this final string they've computed.
So if you don't care for the function be boolean, then you can forget about f and g and just
Yeah. No. It turns out that you still the proof doesn't. Yeah. I think you might get a slightly simpler proof if you just output z itself, and that might work. But then it's a little weird because you're outputting a huge string, so you might think of that as maybe not a completely legitimate counterexample. Yeah, that's true. But anyway, we can do it with booleans, so I'll do it with boolean. Okay, so that's a function. Now, so what is the communication of the trivial protocol for computing this function? So you have time to digest the parameters. And log k, exactly. So the protocol you could just evaluate z, symbol by symbol. Then Alice, in each step, Alice will send a symbol from 1 to k, which is log k bits. And Bob will do the same. And there will be n steps. So it's order n log k bits of communication. So. Yes. Yeah. Okay, so this is the trivial protocol. It takes 2 to the k bits of communication. Okay, so now, so far I've just told you a problem, but I haven't told you what distribution on inputs we're going to work with. And it's going to be a strange distribution. The distribution is tailored towards proving this result. So next, let me tell you what the distribution is. So I'm actually going to define 2 distributions. But let's just define one of them first. So.
Is it possible to make this result to work for worst-case distribution?
Not this function, but in subsequent work, the same authors, Ganor, Cole, and Raz, have gotten results that work for every distribution. Yes. But that's not, what I'm going to show you is for a specific distribution. Okay, so I'm going to define a distribution now in F, these things. So here's how you sample from the distribution. So first, sample a random number j that's uniform from 0 to n minus 1. And next, sample x and y. They'll be sampled independently and uniformly, except they're going to satisfy some constraints. They must evaluate to the same value when the input is of length less than j. Okay, that's the first constraint. And in fact, they must evaluate to the same value as long as the strings that they're working with got the jth step right. Okay, so I'll say what that means. That means also you must have that x of z is equal to y of z when z is of length bigger than j and the jth equation there was correct. Okay, so z sub j plus 1 is equal to x z less than equal to j plus y evaluated as z sub j mod k. Okay. Yeah, for longer z, but it's not just one case, because the number of z's that satisfies this equation is roughly 1 over k fraction of all z's.
So it all, but it's, yeah, so those cases.
Yes. So for roughly 1 over k fraction of the z's, x and y are the same. But in the rest, they're completely independent. Okay?
So for correct z, we just double the value of x, what you say, when we compute z. All of the terms x and y.
Here, yeah. For correct z, most of the time you're just doubling the value. Okay? Okay, and finally, the third step is f. Yes, so I said really you're sampling uniformly from the set of x and y that satisfy these constraints. Okay.
What is z less than equals to j? Is that one string or the collection of j prefixes?
This is one string.
I know the very last sentence, z less than equals to j.
Oh, this is a prefix of length. The prefix of z up to of the first j characters.
So this is actually j constraints.
This z is one string, and this is its prefix of the prefix of the first j characters.
Okay, sorry. This is not all j prefixes that are back up to j.
No, it's just one string. This is one string. So also here, it's the same notation, right? Okay, so I didn't explain. Maybe it's not obvious, but this just means one string of the first. The first are symbols of z.
Probably there should be no strict inequality in one of these cases.
No, it's as written.
So for z equal, so length of z equals to j, you don't require anything.
Yeah, they're independent. That's the crucial point. Okay. So if I had here also for things of length j that they're the same, then Alice and Bob don't need to communicate anything, because they just follow the evaluations of their things, double everything. But they can't do that. They have to communicate something, because in the jth step, they need to get it right. Okay? But they don't know what the jth step is. They don't know which step is the jth step. Okay, so now we have an interesting problem. Okay. Good. Now I need to tell you the last step. So f and g are again uniform such that f of z equals g of z. So in your final string, they're uniform again, but they're equal exactly when the same condition holds, when the jth step is correct. Okay. So for all z where this equation is correct, f and g are equal. Okay. So what I defined actually here is a distribution on inputs that always has the same answer. So the output will always be, in this case, 0. Right? Because if you sample, if you look at the correct z that they're supposed to sample, then certainly it will satisfy the jth equation. Okay? Which means f of z will be equal to g of z.
Wait a minute, what is the correct length? What is correct?
This one. So here in the problem, there's one z, this one that satisfies all the equations. In the distribution, okay, there's the one z. And if you look at that one z, every point in the support of the distribution will have that this will be equal to, so the output is always 0. Okay? So in fact, this distribution is the distribution on inputs that will lead to output 0. So this is, I will call it Q0. And for Q1, I'll just replace this condition with okay, so
If you know if the correct output is always 0, then why do you have to compute that?
you don't. So what is a final hard distribution? It's not the distribution Q0. It's with probability half you sample from this, and with probability half you sample from this. Okay?
The difference between just sample f and g for random?
It's very different, because in both of these distributions, you know that for every z that satisfies this condition, the parity of f and g is the same.
Wait, but there is only one z.
No. There's only one z that satisfies all n of these equations. But there are many z's. In fact, 1/k fraction of them satisfies just this one equation.
Only the last one.
No, only the jth one.
Only the jth one. Okay.
Yes. So to solve this problem on this distribution, you just need to find a z that satisfies just the jth equation. That's what Alice and Bob need to do.
So just so for the probability 1/2 f and g are just chosen independently of each other, or
No. So I've defined a distribution Q0 where it's uniform subject to the constraint. These constraints happen, and there the output will always be 0. And another distribution where the output is always 1.
Oh.
And you pick a convex combination of these two.
Or in that particular, under the same condition.
Yes. Yeah.
It always 1.
Yeah. So the two distributions, both of them satisfy all of those conditions, but in one it's this and one it's this. Okay. So the point is that in both of them, you don't really need to find the true z, the z that satisfies all of these to solve the problem. You just need to find a z that satisfies the jth equation. And if you find a z that satisfies the jth equation, then you output the parity of that z, and it will be equal to the correct answer. Okay.
This is what will remain for low information.
So that's the problem. Okay. N is 2 to the. Okay. So next, I'm going to explain why there's going to be a low information protocol for this problem. That will be relatively easy to at least get some intuition for why that's true. And then the hard thing will be to understand why there's no low communication protocol for this problem. So first, why is there a low information protocol for this problem? So what is the information of the trivial protocol? So if you just send all the z's in this clear, you might think at first that the information of this protocol is actually really small, because most of the time what you're sending is exactly equal to what the receiver is receiving. So he knows ahead of time what you're receiving. So maybe you only learn information in the jth step. So maybe the information is log k. But actually it's a lot higher. Does someone who hasn't seen it before see why it's higher? So actually the trivial protocol that we just discussed, it would reveal k bits of information.
It reveals J also, right?
Exactly, yes. It reveals j. Right? The first time you see that x is not equal to y, you learn the secret, which is at what point were they not equal. And that's because n is so big, that's k bits of information. Okay? So it's not just log k bits of information, you learn the location of this difference. Okay, and j is essentially determined by x and y, so that's a lot of information. But there's a minor variation of that protocol that does have small information. Okay? So the protocol is, in each step, Alice, the trivial protocol, Alice is going to announce x of z. So what she will do now is that with probability 1 minus, it turns out 1 over log n, roughly, she sends x of z. And with small probability, 1 over log n, she sends a uniform string. Okay? So she adds noise to the message that she's sending. Now, suddenly the information you learn is not that much. Because, first of all, intuitively, what do you learn about j? before you learn exactly where j was because you see the first difference. But now if you're Bob, roughly 1 over log n fraction of the whole string is not equal to your input. So you're not sure which of those corresponds to j. Okay, so actually you learn more like log n bits of information from seeing where the mistakes are. Okay, and that's actually something you can prove. So to actually get this to, yeah.
Suppose if you use common randomness, you could just use a permutation of the indices, right? Because all you need to know is that they are you need the order.
Yeah, first of all, you can't permute things. You need to, the actual message depends on what was said before, or where you have to be consistent with the other person about the whole path.
Oh yeah, sorry.
Say,
How you know Z and H step?
we run the trivial protocol. Oh, what is the Z? So Alice will announce some value. In the first step, Alice announces some value, and Bob will announce some value. They will both take the sum mod k of those values, whether they're correct or wrong, and they will commit to those values. So these may not be the right value. It may not be the one that satisfies this. This equation will be violated 1 over log n fraction of the time. But it doesn't matter. All we care about getting right, as I said, is this equation for just one of the steps. And that will be correct except with probability 1 over log n. Okay? So the z you end up with, it will not agree with all of these equations. But with high probability, it will agree with this equation. And that's good enough for this distribution. Because the way we set up the distribution, as long as you get this equation right, then you will get the answer right.
Wait, which equation?
This one. So the way it's... Okay, the way the problem has been set up, the distribution has been set up, there's the real z, which is this z, that agrees with all n equations. And as long as you sample some other z that agrees just in the jth equation, then the parity of f of z and g of z will be the same as the real z. Okay? And that's what we want to output. So you just sample some z that satisfies the jth equation and output the parity. As long as you satisfy the jth equation, you're in good shape. Okay, so your z will have lots of mistakes, but it's okay for computing this problem. Yeah? That's intuitively, yeah. Intuitively, you're going down to a set. No, it takes a proof. It takes a proof. You can bound it, but basically when you add noise that hides information, it's a calculation to show it, but it's short, but I don't want to do it here. Okay, roughly if you say a bit, if you reduce to a set of size 1/2, that's a bit of information. Here's the set of density 1 over log n, that's like log log n. Okay. But what? What? You're asking why something is true that I didn't say is true?
Why lower bound of order of cache should be true for communication?
That's a great question. That's most of the talk. So I haven't gone there yet. That's the hard part, which probably I won't get to. But
yeah, so here you don't. So the two parties are not knowing which one is the true J, but somehow F and G will still pick out the true J.
well, the value of f and g will be correlated at all of these guys with the real j. So the correlations are set up so that happens. So that's what's going on in this example. Okay, so first I will say that this is a lie, that the information is small of this protocol. For what happens is actually if you, in the small probability that you get this jth step wrong, you start to reveal a lot of information. Okay, so what I just said actually does not have a small information, but it can be easily fixed. So it turns out the actual protocol is if Bob starts to see tons of disagreement with his input, which is what will happen if you get this jth step wrong, then Bob will just abort. Okay, and that idea saves the whole thing. So you can abort if you start to see lots of disagreement in a small interval, and together with this, you get a small information protocol. Okay, the information of the protocol will be, turns out, will be like log of k log n, something, roughly. Okay, so that's the information of the protocol. And now I want to say something about how you prove the communication lower bound. As I said, we know the information is small, so somehow that intuition should not translate to the information. And that's what's interesting about it. So, okay, and so the theorem I'm going to prove is that the communication looks like omega k. Okay, you have to send roughly k bits of bits to solve this problem with communication. How am I doing on time? So again, 10 more minutes. All right. All right. Okay, so let's do it. So to do it, I'll first define now a much easier distribution. Like I said, at a high level, the way this is going to work is we're going to switch distributions and argue with a different distribution, and then somehow magically switch back the distributions. So here's another distribution. Okay, so this is a analysis distribution. As before, we'll sample j at random from 0, 1 to the n minus 1. And this time, we'll sample x and y uniformly, but only subject to the constraint that x of z equals y of z when z is less than j. Okay, that's it. So we get rid of all the other conditions. We just sample x and y are exactly the same when z is of length up to j, and then they're completely independent. So it's a simpler distribution. And now I'm going to prove some facts about any protocol that you run on this distribution. And then somehow I'll convert those facts to something about this distribution. So to do this, I'll actually write 3 lemmas which I will need, which I think are kind of independently interesting. I won't explain the proof, but I'll try to explain why they can be used. So the first one is, suppose you have a1 through an, random variables a1 through an and b1 through bn, which are all uniform and independent. Suppose you have j that's a random number from 1 to n, and j is uniform, and these are uniform except that ai is equal to bi for all I less than or equal to j. Okay, so this looks exactly like that. This is kind of the values of the functions on inputs of length 0, 1, 2, so on. Okay, so but for any such random variables, and suppose you have a communication protocol where Alice gets these as inputs and Bob gets those as inputs, then the claim is that you can bound the mutual information between the messages of the protocol. So, okay, so these are messages. Any protocol. Any protocol where Alice gets all the A's and Bob gets B's, you can bound the information that's learned about the jth coordinate, in this sense, by this number. Okay, where this is the length of the number of bits of the messages in total. So you get a bound that's like exponential in the number of bits that are exchanged, divided by n. Okay, and this is essentially the only place where the proof will distinguish communication and information. Because if the communication is small, this number will be small. But if the information is small, I can't say anything about this number. Okay, so somehow, okay, so I'm not going to explain the proof, but it's 4 lines. Okay, so you can try it. It's just the calculations involved. Huh?
It's just some intuitive information.
Yes, but how will you get 2 to the m? That's the question. So it turns out what you need to do is look at each rectangle and the contribution of each rectangle to this term. And you can show that each rectangle contributes roughly 1 over n to this expression. Okay, so each choice of fixing of messages contributes 1 over n, and that gives you this. Okay, so okay, so what does that mean? So a consequence of that means that, so this is lemma 1. So from 1, what you can get, write it here, is that under this distribution that I just defined, this analysis distribution, if you let S be the set of these satisfying the jth equation, then you can bound the mutual information. So this is a random variable, which is the set of z's that satisfy the jth equation. So this depends on x and y. You can show that the mutual information that the messages of any protocol have with S, this is under this distribution, P, conditioned on okay. Can be bounded by the same number. Okay, so okay, so the point is that just that if under this distribution, what you're showing is that basically the players, after communicating, will have small information about which z's satisfy the jth equation. Okay, which is something that you hope would be true if they cannot compute the function. They don't know which z's satisfy the jth equation. Okay. So I'm running out of time, so I'm not sure what to. Okay, so I'll show you one more lemma, and then I will finally try to wave my hands for the rest. So here's another lemma. So the lemma says, suppose you have n independent bits and or n independent random variables, and you have a variable c that's an L-bit string. And S that's a subset of the n coordinates. Okay, so I'll just, so let me give you some intuition. So what I want to bound is this. Okay, so first here's a lemma that follows easily from Scher's lemma. Okay, it says if you have n independent random variables and some c that's correlated with all of them, and that c has L bits of information, and now if you pick S independently of all of these guys, pick a subset of the coordinates, in such a way that the probability that you include the ith coordinate is at most 1 over k, then you expect that if you restrict your attention to just the coordinates of U that are restricted to S, you should get at most L over k bits of information. Okay, because there's L bits of information in total, and you're restricting yourself to a random set, okay, which ignores many of the coordinates. Now, what ends up happening is to do this proof, you need to understand a more complicated situation where S is correlated with C and U. Okay? So what we end up proving is that this is true even if S is not independent, but as long as you have that U, C, and S form a Markov chain, if U, C, and S form a Markov chain, then what you get here is a bound that's something that's that depends on the information between C and S. Okay. This is roughly what you get. Okay. So it says that again, if you have a bunch of coordinates and some C that's correlated with all of these coordinates and they're independent, then even if you sample a collection of coordinates and your sampling is correlated with C and U, as long as U, C, and S form a Markov chain and S has small information, so this means S has small information with all the other coordinates, you can still get something like what you would expect from Scher's lemma. All right, so that's a technical proof, but it means that once you know that M has small information about S, it means that actually M has small information about X projected to S and F projected to S. Okay, so even though these coordinates S and are correlated with the random variables X and F that we're using here, you can use this to show that actually the messages of M do not have any information about the values of X and F on the set of inputs that we care about. Okay. And then there's another technical lemma to complete the proof. But the point is, at this point, basically you can show that M cannot distinguish this distribution P from the distribution Q here. Because from M's perspective, the only way the distribution of X, F, Y, G are different in P and Q is on the coordinates that correspond to this set. Okay? So this distribution which I use in analysis is the same as Q, except P does not satisfy these conditions, right? That X and Y are equal on the jth coordinate. And what you end up proving is that the protocol has no information about those coordinates. So what you can show is that now if you just switch the distribution from P to Q, the protocol cannot really behave any differently.
Unless it is very long.
No. No. As long as this is small, I don't care about the length.
This lemma shows that if M is log n, then you reveal.
The only place where I use the length was here.
Yeah.
And as long as this quantity is small, I can do the switching. Okay, so as long as this information is small, that'll imply that this is small. And now I no longer care about the length of n.
Right.
Okay.
This lemma when M is log n is getting.
Yeah. So as long as these informations are small, then what I'm saying is that, so now it's technical, I haven't proved it formally, but there's a formal way to make what I'm saying, formal. You can then switch this P to Q, and the joint distribution of M, XS, FS, M and the rest of the variables will be roughly the same as what it was before. And that shows that M cannot be computing the value of the function. Okay, so I'll stop there.